hang on 1 second. Sorry, we have some technical difficulties going down on my end. It says that I'm streaming, but I also, let's see. Oh, hang on. Okay, I'm definitely live, which is great. A little bit about my setup here. I stream all my classes from a Surface, and that's how I get the kind of writing thing down. It's a live cast of my screen, but then I use a secondary second computer to kind of monitor the live chat, and that one just froze, which I'm streaming from my Surface. So hello. I am totally live, but it'll take me it'll take me a minute to be fully functional on the live chat. Though I just laughed because Raj, who's my gunner from the first distance education class I ever taught, the one that went live in the middle of the semester, he just popped in and said, hello. Hi, Karen. Right now I have the live chat pulled up on my phone. I'm just waiting for my secondary computer to reboot because it's just more fluid when I can actually use a keyboard for typing. Okay. All right. We are... Whoa, holy moly. Quiet down, computer. All systems are go. This is a, Andrew Jones, to answer your question, this is a chemistry class. It's not a Spanish class. You are totally correct. That's why it says up here at the top, Chem 400 office hours. All right. What was I going to say? Oh, Winnie, how's it going? Good to see you. As promised earlier today. Wow, I feel like I'm... Hello. As promised. Okay, sorry. It felt like I was peeking at my mic, but it looks okay. I'm not going to repeat myself all night. But as I told everybody earlier, we're going to do a review of significant figures. Whoa. My stylus looks really chunky. All right, let's dial it back a little bit. Significant figures. We're going to do a review of sig figs, and then we will, on Monday, do a review for unit conversions. You can ask any of my former students, and there are 2 of them in the live chat right now, how big of a deal I make out of sig figs, and they will probably tell you that I make too big of a deal of sig figs. It is something that I bleed students for points-wise all semester long. So this is something that you really want to get dialed in. You want it to be second nature, like breathing, so you can hit all those points and not have to hemorrhage them. Now, I'm gonna kind of to give you a sense of where we're going. I'm going to give this lecture in somewhat of an inverted order. First, we're going to talk about what are sig figs, or actually, not even that. we're going to first talk about how to identify identifying sig figs. Dude, yes, heck yes. If you don't have to take my word for it, listen to Winnie and Raj. Sig figs never go away as long as I'm teaching. It's so not fun. But what is fun is scoring those 10 points. So that might be a backdoor argument to why sig figs are fun? Question mark. Probably won't hold water in the long run. So we're going to first talk about identifying sig figs. Next, we're going to talk about using significant figures in mathematical operations. All right. And then third and finally, we're going to talk about where they come from and why they actually matter. This is going to be a little bit of reverse order, because I could tell you where they come from and why they matter first. That might make some more sense, but I'm going to give you essentially a mechanical understanding. This is how you identify them. This is how you use them, and then at the end give you a big reason why. So this is not going to take that long. We should be done in like 45 minutes or so, and then it'll just be open office hours season. Okay, so let's talk about identifying significant figures. So let's talk about how to identify them. So I do want to say too, excuse me, that significant figures are often called significant digits. So you'll hear me use both kind of interchangeably. And so significant figures, significant digits, they mean the same thing. So let's talk about identifying which digits are significant. Or I'm going to actually pose that question up here. Whoa, not in green though. Which digits are significant? All right, and the answer to that question is first, all non-zero digits are significant. All right, so that's the first one. If all non-zero digits in a number are significant. So 2 zeros can be significant under 2 circumstances. First, all zeros that are between significant figures are significant. All right, so if you have a zero that is in between 2 significant digits, it is also significant. And then third and finally, I'm going to put this in a different color because this is the one that I see most students have trouble with. This is the one where mistakes are most common. This is the one that's easiest to forget. All zeros that are both, all right, so that's important, that are both to the right of the decimal and at the end of the number. So both to the right of the decimal and at the end of the number are significant. All right, so these are the 3 rules for identifying how many significant digits do you have in a number. All right, so you are counting all non-zero digits, all zeros that are between significant digits, and all zeros that are both to the right of the decimal and at the end of the number. So let's apply these rules and solve some problems together. So let's determine the number of significant figures in the following numbers. All right. So let's take a look at a few examples here. Let's start with the number 10. All right. When you're counting the number of significant figures, first you count every non-zero digit. So we have one non-zero digit. Now for zeros, they're only significant if they are between two significant digits, or if they're to the right of the decimal and at the end of the number. This zero meets neither of those conditions, so there's only one sig fig in 10, in the number 10. All right, let's take a look at 110. Again, same story. You have two non-zero digits. That zero right there at the end of the number is neither to the right of the decimal and at the end of the number, nor is it between two significant digits. So the number 110 would have 2 sig figs. All right, let's do 101. All right, we have 2 non-zero digits, but you'll notice here this 0 is in between 2 significant digits, so it is also significant. The number 101 has 3 sig figs. All right, let's start playing with some decimals. Let's look at the number. Here. Let's do 10.0. All right, here we have one non-zero digit, so it's at least 1 sig fig. You'll notice that we have a 0 that is both to the right of the decimal and at the end of the number, which makes it significant, so that's a 2nd sig fig. The second 0 is between 2 significant figures, so it is also significant. So 10.0 has 3 sig figs. All right. Let's look at 10.00. All right. We have a non-zero digit. We have a 0 that is both to the right of the decimal and at the end of the number. And then these 2 zeros are between significant digits, so they themselves are significant as well. 10.00 has 4 sig figs. All right. Let's mix things up a little bit. Let's do 0.003700. No, let's chop 1 0 off the end. There we go. This number doesn't have to get too long. Now, non-zero digits. We have 2 of them. Is there a 0 that is both to the right of the decimal and at the end of the number? And the answer is yes. There's only one of these. It is right here. Now, for the remaining zeros, these zeros are not in between significant digits, and even though we have 2 of them that are to the right of the decimal, because they're not both at the right of the decimal and at the end of the number, that they're not significant. They have to satisfy both of those criteria. So 0.00370 has 3 significant figures. All right, it is super clutch. Many students will look at these and count them as significant figures. They are not significant. All right, they're not significant because they are just to the right of the decimal. To be significant, a 0 needs to be to the right of the decimal and at the end of the number. Either that or between significant digits. This one is not. All right. Now, so hopefully you've seen this before. This is kind of warming up, bringing back some memories. I want to do a second type of problem. I want to ask you to write the number .30 using ... Part A, I want you to write the number 30 using 3 sig figs. All right. Well, if we're going to do this, 30, just the number 30, only has 1 sig fig. All right. A way to add significant digits to a number is to give it a decimal and a 0. This 0 is to the right of the decimal and at the end of the number, so it's significant. And then this 0 is significant because it's between 2 significant figures, so 30 written with 3 significant figures would be 30.0. Let's go A, B. Let's write the number 30 with 5 sig figs. All right. Well, 30 as a number, it's just like so. If adding 1 0 added after the decimal made it 3 sig figs, well, we could add 2 more and watch what happens. 3 is significant because it's non-zero. The last 0 is both to the right of the decimal and at the end of the number, so it is significant. And the 3 zeros in between are all significant because they are between 2 sig figs. So this would be how you would write the number 30. This is how you would write the number 30 with 5 sig figs. All right, but now let's go for the gusto. And this is actually why I'm doing this problem. Part C. Can you write the number 30 with 2 sig figs? Here we have a little bit of a conundrum. I'm actually going to move this over to the other side of our screen. Here's the pickle we have. If you wrote the number as just 3, 0, this only has 1 sig fig. If you wrote the number and add a 0.0, just 1, this has 3 sig figs. How do you write it with just 2. And the answer here is you have to use scientific notation. All right, scientific notation. If you write the number 30 in scientific notation, it's, it's 3 times 10, right? The way you write a number in scientific notation is you write it as a product of 10, where the decimal comes directly after the first non-zero digit in your number, right? So this is 30 in scientific notation, and if you add a 0.0, now you have 3, a non-zero digit that's significant, and you have a 0 that's both to the right of the decimal and at the end of the number. So this 3.0 times 10 is the number 30 with 2 sig figs. The whole part of scientific notation times 10 to the power of whatever, this does not increase your significant figures. It does not increase the significant figures of your number. So only what is multiplied by the power of 10. So if you wanted to write 30 with 2 significant figures, you'd write 3.0 times 10 to the first. All right? As of this moment in time, we have completed our first objective. Namely, you now know how to identify how many significant digits are present in a given number. We're getting ready to move on to the next part of this lecture, which is using significant figures in mathematical operations. Now this will have an A, this number 2 will have a part A and a part B. A will be multiplication and division. Part B is addition and subtraction. There are different rules for significant figures based on whether you're multiplying and dividing or adding and subtracting. So we'll take these one at a time, starting now. All right, so let's talk about the rules for addition and subtraction. Nope. I take that back. We're going to start with multiplication and division because I think it's easier for most students. Multiplication and division. All right. The rules for multiplication and division are, I feel like they're the more intuitive of the two different sets of operations. All right, and they go like this. When you multiply or divide two numbers, your answer must have the same number of sig figs as the number with the fewest used in the calculation. All right, that is the rule for multiplication and division. When you're multiplying two numbers or dividing two numbers together, your answer must have the same number of sig figs as whichever number you used that had the least. So, using the rules for significant figures, let's perform a couple mathematical operations. Let's multiply 11 times 3. All right. Now, you do 11 times 3. You punch it into your calculator, or you do it in your head. You're gonna know that the answer is 33. Now, this is the correct value, but every time you hit enter on your calculator in this class, you have to ask yourself, train yourself with this question. You hit enter and then ask, but how many sig figs should it have? 33 is the correct value, and we talked in lecture earlier that the correct answer has three parts: correct value, correct number of sig figs, correct units, right? So this is our value, but how many sig figs should it have? And if you look, 11, the number 11 has 2 sig figs. The number 3 has 1. Therefore, our answer must have the same number of sig figs as the number that we used in the calculation, with the fewest. 3 has the fewest. 3 has 1 sig fig. Therefore, our answer should only have 1 significant digit. 3 is going to round down, right? This 3 right here will round down. So our answer, the correct number of sig figs, is 30. All right? 11 times 3 is 30 once you apply the rules for sig figs. Now, this is like fingernails raking across a chalkboard. For most students, if this bothers you on a deep fundamental level, I want to say 2 things. 1, I want you to know that I see you. 2, I acknowledge you're hurt. But I want you to trust me, because there's a good reason for this coming at the end of lecture. All right? So everything inside of you might be screaming that this is so wrong. You need to trust me that it will be okay at the end. All right? Let's just focus on understanding the mechanics of applying these rules, and we'll get to the big question, the why, at the end. All right? Okay. So 11 times 3 is 30 after you apply the rules for sig figs. Now, for those of you who are still deeply upset by this, because you know that 11 times 3 is 33, in this class it's not. But there's a silver lining. If you want 11 times 3 to be 33, then you need to multiply 11 by 3.0. All right? 3.0. Why? Here's why. You'll notice that 11 has 2 sig figs. 3.0 also has 2 sig figs. So you punch this into your calculator and get an answer of 33. Both of the numbers that you used had 2 significant digits, which means your answer must have 2, and it does. So the correct answer for 11 times 3.0 is 33. Eric, let's see. Could you do 3 times 10 inside? Oh, Eric. Yes, absolutely. Let me see. You totally could do that. And you would be totally correct. Absolutely. All right. Let's do a couple more examples. Let's do 87.0 divided by 6.023. All right. Let's see. Cameron, great question. The answer is you don't, and you shouldn't in this case. Whenever you do multiplication and division, oops. You only look at the total number of sig figs in each number. I should say the total amount of sig figs in each number. All right, and you just need to make sure that your answer reflects that in its total number, but the specific decimal places do not matter for division and multiplication. Cameron, what you will see is when we get to the rules for addition and subtraction, that's when decimal places will start kicking in. All right, so we will see that happen. It's just a different set of rules. Now let's do this 87.0 divided by 6.02 0.023. Let's see, 87 divided by 6.023. You are welcome, Cameron. You are totally welcome. All right. If you punch this into your calculator, you will get a very long answer as your value. You'll get 14.444629, and this is the correct value. This is the correct value. We have to ask ourselves how many sig figs. How many sig figs can we keep? 87.0 has 3 significant digits. 6.023 has 1, 2, 3, 4 significant digits. So we've got to roll with whichever is fewer. So 87.0 is what we got to keep. So we can keep 1, 2, 3 significant digits. All right. 4 is going to round down. So the correct answer, the correct value with the correct number of sig figs here will be 14.4. All right, and that is the correct value there. Multiplication and division, same rules. Let's do one more example. 2.3 times 18.9 divided by 400. All right. Now here we've got a mix, but you'll notice we just have multiplication and division. They all have the same rules, right? So because they all have the same rules, we can do this in one giant chunk because the rules for sig figs don't change. They're the same for multiplication and division. So we go 2.3 times 18.9, which is in our numerator, divided by 400. And our value is 0.108675. And when we look at our sig figs, we have 2.3 has 2, 18.9 has 3, and 400 only has 1. So we can only keep one significant digit. You count off the first. 0 is a number that rounds down, so our final answer will be 0.1. This is the correct value with the correct number of sig figs. All right. When you're bundling operations that all share the same rules for significant digits, you do them all at once and apply them at the end. When you have operations that change, like if you're adding then dividing, or if you're multiplying then you're subtracting, then you have to be more careful with the rules and you have to apply them as you go. But here, multiplication and division all the same, so we're good. All right. That is multiplication and division. All right, we're marching forward. We've done part A of part 2. Let's hit up part B, talk about addition and subtraction. All right, addition and subtraction. right, now here's the rule for addition and subtraction. When adding two numbers, I should say, sorry, when adding or subtracting. When adding or subtracting two numbers, your answer must have the same precision as the least precise number used in the calculation. All right. Now, this definition is not as straightforward, mostly because it defines the rule involves this enigmatic thing called precision. Right, it has to have the same precision as the least precise number used in the calculation, and you may not know off the top of your head what that means. And here is a quick rundown of precision. The number with its last significant figure furthest to the right is more precise. So, for example, let's do a couple examples here. Which is more precise? The number 110 or 101? Well, 110 has its last significant digit in the tens place. 101 has its last significant digit in the ones place. Here, the ones place is further to the right than the tens place, which means that 101 is more precise. Let's do a couple other examples. Let's look at 3 versus 3.0, okay? Here are two numbers that have the same value, but different precisions. 3 has its last significant digit in the ones place. 3.0 has its last significant digit in the tenths place. 3.0 has its last significant digit further to the right, so it is more precise. All right? If you compare 10,043 to the number 5,280, 10,043 has its last significant digit in the ones place. 5,280 has its last significant digit in the tens place. 10,043 has its last sig fig further to the right, which makes it more precise. Now, I want to pause for a minute. Often, you may hear professors explain the rules for addition and subtraction by just saying, oh, whichever one has like fewer decimal places, you got to roll with that one. Your answer has to have the same number of decimal places as whatever number you use that has the fewest. Here's why that definition does not work. If you were adding 110 and 101, like right here, neither of these numbers have decimal places. Same with 10,043 and 5,280. Neither of these numbers have decimal places. So how do you apply the rules for sig figs for addition and subtraction when there are no decimal places? You have to understand the full definition, which uses precision. Okay? Now that we know what precision is, let's apply the rules for addition and subtraction. Let's do some calculations with this. So let's go ahead and start by adding, do a new layer. Let's add 101 and 110 together. All right, the value for this sum is 211. All right, but now we need to look at the last significant digit in each number. 101 has its last significant digit in the ones place. 110 has its last significant digit in the tens place. And the rules for addition and subtraction tell us that the answer must have the same precision as the least precise number we use in the calculation. 110 is less precise than 101, which means that 211, our answer, must have its last significant digit in the tens place. 1 is going to round down, so 210 is the correct answer with the correct number of sig figs. All right, let's do another one. Let's do 928 plus 501.5. All right, we add these things together and the sum is 1428.5. That is the correct value. We have to ask ourselves, how many sig figs should this have? And if you look at 928, its last significant digit is in the ones place. If you look at 501.5, its last significant digit is in the tenths place. 501.5 is more precise. So because 928 is less, oh wait, hang on. I messed up with my math. Whoa. 1 plus 8 is 9, right? Okay, yes. Okay, there we go. So because 928 is less precise, we need to round to the ones place because our last significant digit needs to be in the ones place. Here's a problem. So let's round 5 up. That's going to make this 9 a 10, which is going to make this 2 a 3. So 1430 is our answer after rounding. Let me ask you. Actually, I don't want this to be in salmon. All right, after rounding, we get 1430. Let me ask you, where's the last significant digit in 1430? The answer is the tens place. But where does it have to be? It has to reflect the least precise number we use to add. So we need a significant digit in the ones place. The only way you can make that digit significant is by writing this in scientific notation. So we actually can't write 1430 unless we use scientific notation. We got to write this as 1.430 times 10 to the, let's see, we bounce our decimal place over 1, 2, 3 spaces, so this will be times 10 to the third. In 1.430 times 10 to the third, that 0 is significant, so we have the correct precision, correct value, correct sig figs there. All right, let's do one more example with let's do subtraction. Let's do 9.8 minus 4.96. All right, 9.8 minus 4.96 gives us a value of 4.84. As always, we're asking ourselves, how many sig figs should our answer have? 9.8's last significant digit is in the first decimal place. 4.96's last significant digit is in the second decimal place. So we must round our answer to the first decimal place. So this will come out to be 4.8. That's the correct answer with the correct number of sig figs. All right. So that is the rules. These are the rules for addition, subtraction. We've looked at the rules for multiplication and division. What happens when you have a problem, a mathematical problem, where both of your types of operations are present? For example, how do you solve a problem like Maria, if you want to go for a Sound of Music reference? Or how do you solve the following problem? 270 divided by 4 plus 8. All right? You do this by doing order of operations, normal algebraic order of operations. If we're going to solve this expression, we need to first, step 1, solve our denominator. Step 2, or I guess I should say, whoops. Step 1, we need to, solve our denominator, do that addition. Step 2 we'll need to do that division, all right? So if we're gonna do step 1, we have 4 plus 8. 4 plus 8, as we know, is 12. We have to ask ourselves, how many sig figs should it have? 4 has its last significant digit in the ones place. 8 has its last significant digit in the ones place. And guess what? 12 has its last significant digit in the ones place. So we don't need to round. We're good to go. That's step 1. Step 2, we need to divide 270 by 12. All right, I can't do this off the top of my head. That is why calculators are awesome. All right, 270 divided by 12 comes out to be 22.5. All right, now again, we ask ourselves, how many sig figs should our answer have? And now we're doing division, so it's a different set of rules. We're looking at the total number of sig figs. And 270 has 2 significant digits. 12 has 2 significant digits, so that means our answer can only have 2. So we count off our first 2. 5 is going to round up. And so that's going to round that 2 up to a 3. So 23 is the correct answer with the correct number of sig figs. All right. Let's do another example. Let's do let's do 14 times 8 minus 45. All right. Again, order of operations. First, we need to resolve our multiplication inside the parentheses. Second, we're going to handle the subtraction, and we'll have to apply the different rules for sig figs for each different type of operation. So step number 1, 14 times 8. All right. 14 times 8 is 112. All right. Now, when you look at sig figs, 14 has 2 sig figs. 8 only has 1. So our answer can only have 1 sig fig. Now, here's the deal. We're not at the end of the problem, so we need to wait to round. As we move to step 2, in which we have 112 minus 45, we need to remember that our 112 only has 1 significant digit. Its last significant digit is in the... Oh, wait. You know what? In the hundreds place. I am going to... So apologies. I'm going to change our answer here. Mostly because I made this up off the top of my head, and it's going somewhere that I don't want it to. So instead of 45, I'm going to call this 5.0. If you're going, well, wait a minute, I can't do that on a test. The problems that I put on a test, I write, and then I do them myself. They're vetted, whereas this was just kind of made up off the fly. So trust me, I did it for a reason, mostly because I wouldn't have given a problem like that on the exam. So I modified it, I tweaked it in the moment to reflect that. Okay? Okay. Now, 112 is the value, but we're waiting to round to the end of the problem. I put that line to remind myself that this number only has 1 significant figure. All right? Now, 112 minus 5. This comes out to be 107. And now we need to look at our significant digits. 112 has its last significant digit in the hundreds place. 5.0 has its last significant digit in the tenths place. So 112 is less precise, which means our answer must have the same precision. We need to round to the hundreds place. 0 is going to round down. So 100 is the answer. The correct answer, correct value, correct number of sig figs. All right. So those are 2 examples of how you handle mixed operations when you're doing when you have to switch between the rules for multiplication and division and the rules for addition and subtraction. You follow the normal algebraic order of operations, apply the rules for sig figs as you go, but wait to round till the very, very end. All right, that is the correct way to do things. Now, I know I promised that this mini lecture would be done in about 45 minutes, and I was almost accurate. If you look at how we're doing, we just finished part B. Whoops. We just finished part B of number 2. The only questions we have left to answer are, where do sig figs come from, and why? Why do we have to do this? All right. This might take like 10-ish more minutes. And then we'll move on to open office hour questions if there are any. All right, so first, now that we understand how to identify sig figs, how to apply them in mathematical operations, we got to ask, okay, like where do these things come from? All right, and significant digits come from taking measurements. All right, they are all artifacts of measuring. All right, and so here's what I'm talking about. Let's consider a ruler. Let's say this is 0. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll call this 1 centimeter. Let's go up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 centimeters. If I were to ask you to measure a string that's this long, all right, you would go, okay, well, let's see where this crosses paths with the ruler. You know, it looks like it's about right there. It's in between 1.3 and 1.4 centimeters. Now, if you were to say that this string is 1.4 centimeters long, you'd be wrong, right? It's clearly shorter than 1.4. However, if you were to say that this string was 1.3 centimeters long, that's also inaccurate, because you can see that it's longer. It's longer than 1.3. Unfortunately for us, there are no markings between 1.3 and 1.4, so we don't know exactly how far it is. So when you're taking this measurement, you're going to have to guess. I'm going to call this 1.34 centimeters. All right? I don't know that it's exactly 1.34. It could be 1.33, 1.35, 1.32. I have no idea. There are no markings. This space right here is my best guess, and it has a name. This is called the uncertain digit. All right? This is called the uncertain digit. If you were to measure the same string on a different ruler, let's say we measured it on a ruler like this. That only had markings every centimeter. And you're being asked, well, how long is this string? Now, you can see that on this blue ruler, to say that this is 2 centimeters long, clearly wrong, right? It's definitely shorter than 2 centimeters. It's definitely longer than 1. So on this blue ruler, you know it's longer than 1 centimeter, but you don't know how much. You kind of have to eyeball it. And you could call it 1.3, 1.2, maybe 1.4. You have no way of knowing. I'd call it 1.3 centimeters in the absence of having all those little hash marks. All right? This, again, is the uncertain digit. The uncertain digit is always 1 decimal beyond the last mark. All right? If for the blue ruler, the last mark is in the ones place, so the uncertain digit is in the tenths. For the black ruler, the last mark is in the tenths place, so the uncertain digit is in the hundredths, all right? And you can see, if you compare 1.3 centimeters to 1.34 centimeters. This is the difference of 3 sig figs and 2 sig figs. All right? And here's the point. The number of sig figs that any value has is a reflection of the scale, the precision of the device used to take that measurement. The reason why the number in blue is 1.3 and the number in black is 1.34 is the black ruler is more precise. It has a more precise scale. It has tinier markings, so you get more information in the form of significant figures. All right? The blue one you get less, because look at that ruler. Like, whoever made that was lazy. They only put markings at each centimeter. It's going to be it's not going to be as precise. All right? So that is why significant figures matter. They're there because they reflect the device that was used to make that measurement originally. And devices can be very precise, and then they can be very crude, right? And so the more sig figs you have in a number, the more exacting that instrument was that made that measurement initially. All right? Now, I want to use this newfound understanding of where they come from to address why applying the rules for sig figs matter in a calculation. So that's where they come from. Let's talk about why we apply the rules for multiplication, division, for addition, subtraction. Let's do it using the what I consider to be one of the most disturbing examples in all of mathematics. Let's take 510,000 grams, and let's add 500 grams to it. Well, you do the correct value, the answer to this problem is 510,000 and 500 grams. But now let's apply the rules for sig figs. 510,000 has its last significant digit in the 10,000s place. 500 has its last significant digit in the hundreds place. Which one's less precise? Well, 510,000. That means our answer must have must have its last significant digit in the 10,000s place, and 0, as we know, rounds down. So the answer to the sum of 510,000 plus 500 is 510,000 grams. All right? And this is where I see students throw up their hands in frustration and say, this doesn't make any damn sense. You can't add 500 grams to something and not have it add. You know, like the outrage is real, and I get it, right? Because 500 isn't nothing. But here's the question I want to pose to you, all right? Here's the question I want to pose to you. I want you to think of where this number came from. Because this right here is the uncertain digit. The uncertain digit for this number is in the 10,000s place. What does that mean? That means that the device that was used to make this measurement, cannot tell the difference between 514,000 grams all the way down to 509. No, sorry. That's not true. 505,000 grams. The number, the mass of whatever this was, this device that measured it, could have a mass anywhere between 514,000 and 505,000. All right? This is, we're talking about right here. This range is a 9,000 gram range. And compared to 9,000 grams, 500 is insignificant. All right? This is not significant. Compared to 9,000. All right? The inaccuracy in a device that cannot tell the difference between 514,000 and 505,000 grams is gigantic. That's a huge swath of masses. So adding 500 grams to this number is meaningless because this number was measured with a device that was terribly imprecise. Now, if you want your 500 grams to matter, then take it a measurement, a mass measurement with a device that's actually worth something. Like maybe one that measures to the 10th place. And add 500 grams to 510,000.0 grams. Let's try this on for size. If you add these two together, it'll come out to be, well, 510,500 grams. Let's look at our significant digits. 510,000.0 grams has its last significant digit in the 10th place. 500 grams has its last significant digit in the hundreds place. Therefore, our answer must have its last significant digit in the hundreds place. So there is your answer. All right, that's why sig figs matter. They keep us from adding meaningless numbers. Adding a very small number to a number with huge error bars doesn't have any physical meaning, and so it grounds our calculations in the devices that were used to take those measurements. All right, so hopefully this kind of gave you a taste of why this matters, where they come from, why we need to do them, because chemistry is a physical science, which means we are taking measurements out in the world, and the devices that we use to measure affect the amount of information that makes it into our data. All right, so that is the official end of our sig fig mini lecture. I said I was going to do 45, and looks like it did an hour and 10. So that is 25 minutes of false advertising. So that is that. Now this is this. That is the sig fig mini lecture. At this point in time, we are going to open things up to, so now it's just open office hours time. I am down to maybe draw a better A. That's a cooler looking A. Are there any questions out there? If there aren't, I'm going to do things like check emails and build Canvas pages. But I am totally interruptible. I would much rather be talking chemistry and answering any questions you may have. So hit me with them if you have any. I'm going to check my email to see if anybody submitted any questions ahead of time. But this is the official end of the mini lecture. Okay, let's see. Do we always have only one digit before the decimal place when using scientific notation? Andrew Jones. Excellent question. And yes, the short answer to your question is yes. For scientific notation, the definition of scientific notation is there can only be. Actually, I shouldn't say there can only be. There must be. Let's change this around. There must be only one non-zero digit before the decimal. So, for example, if you had the number 6,735, right? You could also write this as, if you took this and bounced it over 1, you could write this as 673.5 times 10, or if you bounced it over again, you could write this number as 67.35 times 10 squared. You bounce it over one more time. You could write this number as 6.735 times 10 to the third. That being said, this last one is the only, even though all of these numbers have the same value, this last one is the only one in scientific notation. Because in scientific notation, there's only one non-zero digit before the decimal place. So to get a number directly into scientific notation, you find where the decimal is and move it, in this case 1, 2, 3 spaces over, so that it places the decimal right after your first non-zero digit, and then you multiply by the appropriate power of 10. So in this case, 10 to the third. Correct. Okay, yes, Andrew, excellent example. Let's dig into this a little bit. Let's look at 8.0 times 10 to the first. This is not scientific notation because you've got a 0 in front of the decimal place. But you'll notice that if you actually multiply this out, this is just the number 8, all right? So this is not, the first one is not scientific notation. The second one is not scientific notation because there's no power of 10 involved. So technically, the way you write 8 in scientific notation is, it's going to be 8 times 10 to the power of 0. This is scientific notation. Because you've got the power of 10 in there, and the first non-zero digit in the number 8 is 8. So if you were thrown something like, write 8 in scientific notation, it'd be 8 times 10 to the power of 0. Because, again, if you have any number raised to the power of 0, it is just equal to 1. This is a fun little algebraic snack. Great questions. Yeah, totally. Thanks for bringing those up, because those are going to be broadly applicable to everybody. Scientific notation and sig figs go together like peaches and gravy. Of course, you are most welcome. Yeah. Okay. You will be able to find, so those will be uploaded to the lab Canvas page soon. I don't know why I put an at. Just soon. Very soon, like as in like tonight or tomorrow is when they'll be going up. You too. Alrighty. So those are the scientific notation, or a couple scientific notation questions